Hello there. Now we'll be looking at electric polarizability. So here is the case. Let's say there is an atom with a nucleus and an electron, where the nucleus has a charge of plus E and the electron has a charge of minus E. See, it's nice. It's a neutral atom. But then here we're considering an electron cloud with charge density rho, which is given here, total charge by total volume. The radius of this atom is A, but the net charge is centered at the nucleus. So finally, it's a neutral atom. This is the case when there is no external field applied. Now let's suppose there is some E external applied, and let's say we place this atom in that applied electric field. Let's suppose the nucleus gets displaced by a distance of d from the center, because electric field will cause this, right? Positive charges will go along the electric field and negative charges will go in the opposite direction of the negative field. So plus E will go to the right and minus E will go to the left. The cloud will shift to the left, so the central effect, whatever is there, will the center point will also move to the left. But for our convenience, we'll assume that the negative charge is not moving anywhere. We'll assume that the net negative charge is still at the center only, but then the positive charge, which is the nucleus, it got displaced to the right by a distance of d. So because of some external applied field, a dipole moment is induced. So this is one concept. If you apply an external electric field, a dipole moment is induced in a neutral atom. Okay, now what do we do with this? I'm not applying a very high electric field, in the case of which this nucleus will get displaced in such a way that d will become greater than the radius of the atom. That means the atom is going to get ionized and the electron and the nucleus will get separated. We are not applying such high fields. We are applying normal electric field, so this d is smaller than a. So when will this not go away, and when uh, so just it's an equilibrium. When the nucleus is not going anyway, when it's staying in the place where it is staying, it's in equilibrium. That means all the forces acting on it, uh, when you sum up all the forces acting on the nucleus, the net is zero. That is what all of this is telling. You have nothing much in this slide. So here is, we've seen that the magnitude of the externally applied electric field and the magnitude of the electric field experienced by the nucleus due to the electron cloud is equal. Both of them have the same magnitude because the nucleus is in equilibrium. Now let's suppose now, how do we find out the electric field due to the electron cloud, which we conveniently assume to be in the center, right? When even though when it's supposed to move to the left in the presence of an externally applied electric field, we're assuming it's in the center for our convenience, for calculation purposes. So let's say we remove the uh, nucleus for a while, and now we'll try to find out the contribution of electric field in the atom due to this negative charge, which is due to the electron cloud. So I'll apply Gauss law, take a distance r. I'll take a Gaussian surface with radius r, which is a sphere in this case. Just apply Gauss law. What I'll get is I'll get electric field due to the uh, electron cloud within this Gaussian surface. So electric field at a distance r is given by this equation. A is the radius of this entire atom, at atomic radius. So now we got the electric field due to the electron cloud as well. Now if I just look at the magnitudes, we know both of their magnitudes are equal. Externally applied electric field as well as the electric field due to the electron. So since I'm taking magnitude, the minus sign is going to go away, and instead of r there is a d here, because that is the distance of separation between minus c and plus c, the length of the dipole. And dipole moment is given by E into d bar. Since I'm taking magnitudes, it's just ED. If you compare these two equations, we'll get this one. Uh, Dipole moment is proportional to electric field. So the constant of proportionality is called polarizability. It's denoted by alpha. In this case, it is 3 times volume into epsilon naught. Epsilon naught is the permittivity of free space. Apparently, see, this is a very crude approximation, but then this model is very crude. That is what I wanted to say. But then experimentally, it is shown that this 3v epsilon naught is it gives quite a good answer. Even though the model is very crude, it gives a very nice answer. Up to some decimal places, it gives the accurate answer. Uh, so in general, dipole moment is proportional to the applied electric field. So the proportionality constant is the polarizability. In general, I said in general. So in general, this alpha is a tensor. It's not a scalar. It's not a vector. It's a tensor. In the previous case, it's just a scalar. It's just a number here, 3v epsilon naught, where v is the volume of the atom. But this dipole moment and all, it is also applicable to complex molecules, 3D molecules, CO2 and whatever. You have all kinds of things. So in general, this alpha is a tensor. So this is how a tensor looks like. A scalar is just a number. A vector is a column matrix. A tensor is a matrix in general. It looks like this. A two rank tensor. If it were a three rank tensor, you would have gotten a 3 by 3 by 3 matrix, a 3D matrix with 27 components. This alpha has 9 components. But, anyways, it is none of our concern. Yes, none of our concern, anyways. So, now we'll look at this one. Let's say there is a polarizable object. The, Initially, all the dipole moments within it will be randomly aligned. Once you apply an external electric field, all the dipole moments inside it will align themselves along the externally applied electric field. That is what is happening here. One example is this one. If you take a capacitor and place some polar material, some dielectric, something of that sort. So due to this externally applied electric field, all the dipole moments inside this will get themselves aligned along this electric field. So if you look at it, some positive charges are getting accumulated on the top and negative charges are getting accumulated on the top. This will result in some electric field from top to bottom, some E induced, some electric field is induced that is opposing the applied electric field because both of them are in the opposite directions. So I can say electric field decreases and potential also decreases in the sense that uh, both of them have the same magnitude. I'm looking at the magnitudes, I'm not looking at the directions. So this minus sign will not cause us a problem. So if A decreases, V decreases as well. And capacitance of this capacitor and the potential across it, they have an inverse relationship. So as V decreases, capacitance increases as well. Nice, this is one example. Now moving on, let's see what is the effect of placing a dipole, one single dipole. Now we're not placing a polar material or polarizable object or whatever. We're just placing one single dipole in an externally in an like electric field. Yes, there's an external electric field somewhere, and then we place a dipole there. Dipole is this green line. You see a positive charge q and a negative charge minus q. I mean, we know all of this. Since this is a positive charge, a force will be applied on the right side. It's going to go towards the electric field in the direction of the electric field. Since this is a negative charge, it's going to go in the opposite direction of the yes. This is all of this is fine. So if you do some derivation, you'll find that uh, this dipole moment is rotating. It is From here, it's rotating. It's going from here to here. It's going like this way. The rotation is in this direction, clockwise direction. Yes, searching for that word. The dipole rotates clockwise in clockwise direction. In this case, if you do the derivation, we know torque is nothing but r cross f. You do all this derivation, you'll reach at this point. Torque experienced by a dipole is nothing but dipole moment cross electric field. Let's see what is the potential energy. But before looking at what is the potential energy, we'll just look at the work done. See, if you've watched the previous videos, you must have seen the same thing in work and energy in electrostatics. Work done against something, work done against the force due to electric field, work done against electric field. So we're doing the same thing here. Work done against the torque. What kind of torque? Torque due to the electric field. So work done against the torque due to electric field to bring dipole from some theta 1, it's in this configuration, to some other configuration where the angle is theta 2 and theta 2 is greater than theta 1. It means it's going in an anti-clockwise direction. So that is the direction, anti-clockwise direction. But we know that torque is clockwise direction in this case, whatever case we've taken. In the general case, it's going the clockwise direction. So if you do, how do I find work done? How do I find this work done? I just have to do dot product, uh, torque dot. This is like the force, and this is like uh, displacement. This is angular displacement, and then I have some torque here, which is the angular version of force from theta 1 to theta 2. So this is against, so it will be the negative of torque due to the electric field. And if I look at the dot product, uh, angular displacement is in the opposite direction of the torque due to electric field. So their dot product will result in this minus sign. So minus minus cancel, and you do integration, you'll get this one anyways. So potential energy has a definition. It's just that potential energy of a dipole is given by work done against this torque to bring dipole from pi by 2 to theta. Why pi by 2? It is by convention. It is by convention. This is the definition. So if you use this, what you'll get is potential energy, which is nothing but minus dipole moment dot electric field. This is by convention. This pi by 2 is by convention. There is no magic or whatever. It's just convention. If you choose a different convention, then I mean, this is the form. You can choose whatever convention you want. But for in this case, it's pi by 2. At pi by 2, my potential energy is supposed to be 0. That is the convention. Oh, we are done with this. There's nothing much to be told here. Uh, yes, thank you. Yes, thank you very much.